December 18, 1944, Belgium, 0547 hours. Staff Sergeant Karl Wrench Eriksson stood in neat deep snow, staring at 12 frozen Sherman tanks that refused to start. Behind him, the sounds of German artillery grew closer with each passing minute. The entire armored column, 47 tanks, 3,000 men, and the only relief force within 50 miles of surrounded American troops, sat motionless in the pre-dawn darkness. Engineers had tried everything. Battalion commanders were screaming into radios, and somewhere to the east, men were dying because these machines wouldn't move. Eriksson had 30 minutes, maybe less. What happened next? A repair so unorthodox that it violated every Army technical manual, so improvised that it shouldn't have worked, would become legend among tank crews. But the story of how one Iowa farm boy saved an entire armored column isn't just about mechanical genius under pressure. It's about a fatal design flaw that nobody saw coming, a problem that nearly cost the Allies the Battle of the Bulge, and a solution so brilliantly simple that it would make engineers shake their heads in disbelief for decades to come. But to understand how Eriksson pulled off the impossible in 30 minutes, we need to go back to where this problem began. Not in the frozen Belgian forest, but in the Detroit factories where these tanks were born, and in a design choice that seemed perfectly reasonably until winter came. The M for Sherman tank wasn't supposed to fight in European winters. When Chrysler, Ford, and Fisher Body started mass-producing Shermans in 1942, they were building for a different war. North Africa, the Pacific, places where heat was the enemy, not cold. The Sherman's Continental are 975 radial Injuna, 9-cylinder air-cooled beast borrowed from aircraft. Design performed beautifully in the desert. It was reliable, powerful enough to move 30 tons of steel at 25 miles per hour, and simple enough that mechanics could maintain it with basic tools. But air-cooled engines have a particular vulnerability that doesn't show up in technical specifications. They depend on precise tolerances, microscopic gaps between pistons and cylinders that allow metal to expand when heated. In normal operating conditions, these gaps disappear as the engine warms up, creating a perfect seal. But in sub-zero temperatures, metal contracts, those carefully calculated tolerances become too wide. Oil thickens into something resembling molasses, and if you try to crank the engine when everything's contracted and sluggish, you're asking for catastrophic failure. The Army knew this, of course. Field Manual 7-20 specified cold weather starting procedures: warm the oil, heat the engine compartment, run auxiliary heaters for 20 minutes before attempting ignition. Under ideal conditions, with proper preparation, a Sherman could start in temperatures down to -10 degrees Fahrenheit. December 1944, in the Ardennes forest, was not ideal conditions. The winter of 1944 would become the coldest in European recorded history. Temperatures plunged to -16 degrees Celsius, about 3 degrees Fahrenheit. Worse, the German offensive that would become known as the Battle of the Bulge had caught American forces completely by surprise. Units were scattered, supply lines disrupted, and those auxiliary heaters the manual specified, they ran on fuel that was suddenly in very short supply. Lieutenant Colonel Harold Benson commanded the 47th Armored Regiment, part of the 4th Armored Division, racing north to relieve surrounded troops at Bastogne. His column had been rolling hard for 18 hours when they stopped to refuel and regroup in a small Belgian village called Hebel. It was supposed to be a 90-minute halt, then the engines wouldn't restart. It was like they'd been turned to stone. Benson would later write in his after-action report, "We'd shut them down for 45 minutes, and when the crews tried to fire them up again, nothing. Dead as a doornail. A dozen tanks, and we couldn't get a single damn one to turn over." This wasn't just an inconvenience. This was catastrophic. The 101st Airborne was encircled at Bastogne, running low on ammunition, food, and medical supplies. They'd been holding off German tank divisions for 2 days, and they were begging for relief. General Patton had promised them help would arrive within 48 hours. The 4th Armored Division's Combat Command B was that help, and if they couldn't get moving, thousands of paratroopers would be overrun. The battalion's motor pool sergeant, a meticulous engineer named William Hartley from Massachusetts, tried everything in the book. They drained oil pans and heated the oil over open fires, then poured it back and still warm. They wrapped engine compartments in blankets and tarps, building small fires underneath the tanks. They even tried one of the old trucker tricks, pouring gasoline into the oil to thin it out, hoping the engines would start long enough to warm up properly. Nothing worked. What Hartley didn't know, what nobody in the field knew yet, was that they were dealing with a perfect storm of mechanical problems. The extreme cold had caused the oil to gel, the fuel lines had ice crystals forming in them, and the engine blocks themselves had contracted so much that even hand cranking couldn't generate enough compression to fire the cylinders. By 0530 hours, Hartley was out of ideas. Lieutenant Colonel Benson was on the radio with division headquarters, trying to explain why his relief column wasn't moving, and the German artillery that had been harassing them all night was getting closer, zeroing in on their position. That's when someone remembered the kid from Iowa. Karl Eriksson wasn't supposed to be there. At 23 years old, He was a replacement one of thousands of young soldiers rushed to Europe after DID to fill out depleted units. He'd grown up on a dairy farm outside Des Moines, the kind of place where you learned to fix machinery because the nearest mechanic was 30 miles away and you couldn't afford to let anything stay broken. By age 12, Erickson could rebuild a tractor engine blindfolded. By 16, he'd figured out how to jury-rig a broken thresher using parts from a Model T, Ford, and baling wire. When he enlisted in 1943, the Army took one look at his AGCT scores and tried to send him to officer candidate school. Erickson turned them down flat. "I fix things," he told the recruiter. "That's what I'm good at. That's what I want to do." They made him a tank mechanic and sent him to the 4th Armored Division's 126th Armored Ordnance Maintenance Battalion. He'd been with the unit for exactly 6 weeks. Staff Sergeant Hartley found him under one of the frozen tanks, lying in the snow, listening. "Erickson, get up, we've got a situation." What Hartley explained sounded impossible. A dozen frozen engines, no time, no proper equipment, and the weight of an entire relief operation sitting on their shoulders. The experienced mechanics had already exhausted every standard procedure. The engineers from division had radioed back suggestions that required equipment they didn't have and time they couldn't spare. Erickson listened carefully, then asked a single question. "Sergeant, you still got those engine blocks from the shot-up tanks we salvaged last week?" Hartley blinked. They did, in fact, have 3 damaged engine blocks loaded on one of the recovery vehicles. Shermans that had been knocked out by German fire but whose engines were mostly intact. They were supposed to be shipped to depot maintenance for rebuilding, but nobody had gotten around to it yet. "Yeah, we got him." "Why?" "Because I think I can get your tanks running, but I'm gonna need a blowtorch, about 60 feet of copper tubing from the radio trucks, and you're gonna have to trust me to do something that's probably gonna get me court-martialed if it doesn't work." It was 05 for 7 hours. Artillery shells were starting to land less than a kilometer away. Lieutenant Colonel Benson gave Erickson 30 minutes and told Hartley to give him whatever he needed. What Erickson had realized lying in the snow, listening to the absolute silence of those dead engines, was that they were thinking about the problem backward. Everyone was trying to warm up the cold engines, but that was slow, inefficient, and required resources they didn't have. What if, instead, you used heat that was already there? What if you could transfer thermal energy from something that was warm to something that was cold, rapidly and directly? Those salvaged engine blocks had been inside heated recovery vehicles for days. They weren't running, but they weren't frozen solid either. They held residual heat. Erickson's plan was audacious. Use the warm engine blocks as giant thermal batteries. Connect them to the frozen engines with a copper tube filled with heated water, basically creating a crude but effective heat exchange system that would warm the frozen engines just enough to restore those critical tolerances. "Sergeant," Hartley stared at him. "Kid, that's completely insane." "Yes, Sergeant, probably is. It's not in any manual I've ever read." "No, Sergeant, it's not. If you crack one of those engine blocks by thermal shocking it, we're down another tank permanently." "Yes, Sergeant, that's a risk." Hartley looked at the sky, where the first hints of dawn were beginning to show. They could hear small arms fire now, mixing with the artillery. He made a decision that would either save the column or end his career. "Do it. You've got 28 minutes. What followed was organized chaos. Erickson grabbed 2 privates from the motor pool and sprinted to the recovery vehicle. They manhandled one of the salvaged engine blocks onto a dolly 600 pounds of cast iron and steel that fought them every inch of the way. Meanwhile, other mechanics stripped copper cooling lines from damaged radio trucks, creating a serpentine network of tubing. The plan was brilliantly simple in concept, nightmarishly difficult in execution. First, they'd heat water to just below boiling, using a blowtorch and the tank's own auxiliary fuel. Then they'd pump that water through copper tubes, snaked around the warm salvaged engine block, which would heat the water even further. Finally, they'd route those tubes into the frozen engine compartments, specifically around the cylinder heads and oil pan, creating a rapid heat transfer. Did you know that copper is one of the best thermal conductors available? It transfers heat nearly 400 times better than air. That's why plumbers use it, why electronics manufacturers use it for heat sinks, and why Erickson knew it would work for this improvised field repair. The Army used copper extensively in vehicle radiators and oil coolers. He was just repurposing that technology in a way nobody had thought of before, but knowing the theory and executing it in 28 minutes in sub-freezing temperatures, while under artillery fire, are very different things. Private James Morrison from Ohio held the blowtorch steady, while Erickson wrapped copper tubing around the salvaged blocks' cylinder heads. The metal was so cold it burned their hands even through gloves. Private Eugene Vasquez from Texas ran between tanks, measuring lengths of tube, connecting sections with compression fittings salvaged from hydraulic lines. "This is never gonna work," Morrison muttered, his breath creating clouds in the frozen air. "We're building a Rube Goldberg machine in a war zone." "Rube Goldberg's machines always worked in the end," Erickson said, not looking up from his welding. "That's the whole point of the joke." At 0559 hours, the first system was complete. Ericsson's hands were shaking partly from cold, partly from adrenaline, partly from the realization that he was about to test a theory that could either save thousands of lives or accomplish absolutely nothing. They fired up the blowtorch and started heating water in a steel drum. The principle was sound. Hot water would circulate through the copper coils wrapped around the warm salvaged engine block, picking up additional heat. Then it would flow through tubes running directly into the frozen Sherman's engine compartment, transferring that heat to the critical components. In theory, it would warm the engine block enough to restore those microscopic tolerances, thin the oil sufficiently for the starter to turn the engine over, and melt any ice in the fuel lines. In theory, Ericsson watched the temperature gauge he'd jury-rigged from a meat thermometer. When the water hit 180 degrees Fahrenheit, he gave the signal. Morrison opened the valve. Hot water began flowing through the copper network. Nothing happened. 30 seconds passed. Morrison looked at Ericsson. Ericsson stared at the frozen Sherman, trying to will it back to life through sheer determination. 40-5 seconds. Kid, I don't think Hartley began. Then they heard it. A sound so subtle that you'd miss it if you weren't listening. A faint tick-tick-tick as metal began to expand. The thermal transfer was working. Give it 2 more minutes, Ericsson said. The heat needs time to penetrate. They were out of time, and he was asking for 2 more minutes. Artillery shells were landing close enough now that they could feel the concussions. Lieutenant Colonel Benson was yelling at everyone to mount up, to get ready to move, to do something. Ericsson waited. He counted to 120, ignoring everything else, trusting the physics. Then he yanked the tubes free, threw open the Sherman's access panel, and yelled at the crew, "Start her up." Now, the tank commander hit the ignition. The starter motor whined. The engine coughed once, twice, and then, with a roar that sounded like the voice of God himself, the Continental R975 engine fired to life. 12 men cheered. Hartley grabbed Ericsson by the shoulders, shaking him. Lieutenant Colonel Benson, standing 50 yards away, actually smiled for the first time in 3 days. But one tank wasn't enough. They had 11 more frozen machines and maybe 20 minutes of relative safety left. "Everybody who knows how to use a wrench, get over here," Ericsson shouted. "We're gonna run this play 11 more times, and we're gonna do it faster." What happened over the next 18 minutes would become a legend, whispered about in motor pools and maintenance depots for the rest of the war. Ericsson turned his improvised heat exchange system into an assembly line. They'd heat one tank while prepping the next, moving the salvaged engine block from vehicle to vehicle on the dolly like a faith healer at a revival meeting. Other mechanics, watching the first success, grabbed every blowtorch and copper tube they could find. They stripped parts from damaged vehicles with the efficiency of someone found a second working engine block. Someone else figured out how to speed up the water heating by using 2 blowtorches instead of 1. Tank after tank roared to life. At 0617 hours, with German reconnaissance elements less than 2 kilometers away, the 12th and final Sherman fired up its engine. The entire column was mobile again. Lieutenant Colonel Benson didn't waste time with congratulations. "Move out. Combat formation. We've got paratroopers waiting for us." But here's what makes this story truly remarkable. Ericsson's field modification didn't just save one column on one frozen morning. Word spread through the 4th Armored Division like wildfire. By the time Combat Command B reached the outskirts of Bastogne on December 26, breaking through German lines to relieve the 101st Airborne in what historians would call one of the most dramatic rescues of the war, every mechanic in the division knew about Ericsson's heat trick. Within 48 hours, ordnance battalions across 3rd Army were implementing variations of his improvised thermal transfer system. But the real validation came from an unexpected source. On January 3, 1945, Ericsson was summoned to division headquarters. He assumed he was finally getting court-martialed for the unauthorized field modifications. Instead, he found himself face-to-face with 2 engineers from Aberdeen proving ground the Army's premier weapons testing facility and a full colonel from Army Ordnance Command. The colonel got straight to the point. "Sergeant Ericsson, we need you to explain exactly what you did to those frozen tanks, and we need you to explain it in detail, because what you accomplished shouldn't have been possible." What followed was a 3-hour technical debrief that would fundamentally change U.S. Army cold weather operations. The engineers from Aberdeen had been working on the cold start problem for months. They knew the Sherman's air-cooled engine struggled in extreme cold. They'd designed elaborate preheating systems, auxiliary combustion heaters that weighed 80 pounds, required special fuel, and took 45 minutes to warm an engine sufficiently. These systems were effective but logistically nightmarish. They were being manufactured in limited numbers and deployed to units based on priority. Ericsson had accomplished the same result in less than 3 minutes per tank, using salvaged parts and basic thermodynamics. "The thing is, sir," Ericsson explained, "I wasn't trying to invent anything. I was just trying to move heat from where it was to where it needed to be. The salvaged engine blocks were thermal massed, basically big hunks of metal that held residual heat. The copper tubing was just a highway for moving that heat around, and water's a great heat transfer medium when you keep it moving. The colonel nodded slowly. And it occurred to you to do this. Under fire, in the dark, with no testing or preparation. Well, sir, it wasn't that different from what we did on the farm when the tractor wouldn't start in winter. My dad used to warm up the engine block by draining hot water from the house through a hose. I just adapted the principle. One of the Aberdeen engineers actually laughed. Sergeant, we've had 15 PhD physicists working on this problem for 6 months, and you solved it with farm knowledge and scrap metal. But there was more to it than simple ingenuity. What Ericsson had accidentally discovered was a truth that the Army's engineering establishment had overlooked. Complex problems don't always require complex solutions. The preheating systems being developed at Aberdeen were marvels of engineering, carefully calculated, precisely manufactured, thoroughly tested. They worked, but they were also expensive, fragile, and dependent on supply chains that could be disrupted. Ericsson's system was crude, ugly, and violated multiple technical regulations. It was also fast, adaptable, and could be built from materials available in any motor pool. The colonel made a decision that would ripple through Army logistics for the remainder of the war. We're issuing a field modification notice. Every armored division in Europe is going to get copper tubing, compression fittings, and instructions for implementing what we're calling auxiliary thermal circulation systems. He looked at Ericsson. You're going to write those instructions. Did you know that by war's end, variations of Ericsson's improvised heating system were being used by armored divisions from the Rhine to the Pacific? Field reports documented hundreds of instances where disabled vehicles were brought back to operational status using the technique. Some units refined it further, creating semi-permanent installations with dedicated pumps and heater elements. Others kept it simple and crude, staying true to Ericsson's original design philosophy: use what you've got, move fast, get it done. But the immediate impact that frozen morning in Belgium was what mattered most. Combat Command B's relief of Bastogne on December 26 became one of the defining moments of the Battle of the Bulge. Historians often focus on the heroism of the 101st Airborne Defenders, or General Patton's remarkable 90-degree pivot of 3rd Army. They rarely mention that the relief force almost didn't arrive at all because their tanks wouldn't start. Lieutenant Colonel Ben's after-action report was matter-of-fact. 05 for 7 hours. Encountered mechanical difficulties with multiple vehicles due to extreme cold weather conditions. 618 hours. Issues resolved through field expedient repairs. 623 hours. Column resumed. Movement toward objective. Issues resolved through field expedient repairs. 12. Words to describe a 30-minute engineering miracle. But the men who were there remembered differently. Private Morrison, the kid who'd held the blowtorch and doubted it would work, later wrote in a letter home, "Mom, I saw something yesterday I still can't quite believe. We were dead in the water, sitting ducks, and this farm kid from Iowa basically invented a solution out of thin air and spare parts. The brass keep talking about superior American technology and industrial might, but what I saw was superior American improvisation. We had a guy who understood how things work, really work, not just what the manual says. And when the manual didn't have an answer, he made one up." Captain Robert Hayes, Benson's operations officer, put it differently in his personal journal. Ericsson didn't just fix 12 tanks. He bought time that we didn't have, solved a problem nobody else could crack, and did it with the kind of practical genius that you can't teach in any school. If we win this war, and after today, I think we will be, because we've got 10,000 guys like him who know how to make things work when they shouldn't. The impact extended beyond that single frozen morning. In late January 1945, when elements of the 3rd Armored Division got bogged down near St. Vith during sub-zero temperatures, they used Ericsson's method to resurrect 23 disabled vehicles in less than 4 hours. In February, when the 9th Armored Division pushed toward the Rhine in what would become some of the coldest combat operations of the European War, their ordnance battalions credited the thermal circulation technique with maintaining operational readiness, rates above 80% unheard of for cold weather armored operations. But perhaps the most telling validation came from an unexpected source. Captured German maintenance reports. WEHR, MACHT tank units had been dealing with cold start problems on their own. Vehicles, particularly the temperamental Maybach engines in Panthers and Tigers. German engineers had developed similar heating systems, but they were complex, requiring specialized equipment and trained technicians. When German intelligence obtained a captured American field manual describing Ericsson's technique, their analysis was brutally honest. The American approach sacrifices engineering elegance for practical effectiveness. Their field mechanics possess a degree of improvisational capability that our doctrine does not encourage. This represents a significant operational advantage. In other words, the Germans built better tanks, but Americans were better at keeping them running. The war in Europe ended on May 8, 1945. Staff Sergeant Karl Eriksson was in Germany when it happened, still serving with the 126th Armored Ordnance Maintenance Battalion. He'd been recommended for the Bronze Star for his actions in Belgium, but the paperwork got lost somewhere in the chaos of the final offensive. He didn't particularly care. The tanks ran, the men survived. That was enough. He came home to Iowa in October 1945, used the GI Bill to study mechanical engineering at Iowa State, and spent 40 years designing agricultural equipment. He rarely talked about the war. When pressed, he'd mention the cold, the noise, the fear, but almost never the 30 minutes that made him a legend among tank crews. It wasn't modesty. Exactly. It was something more fundamental to how Eriksson understood the world. Problems existed to be solved, and you solved them with whatever tools you had available. Making a big deal about it seemed to miss the point entirely. The people around him, though, understood the significance. Sergeant William Hartley, who'd given Eriksson permission to try his crazy idea, stayed in the Army after the war and retired as a master sergeant in 1962. In his retirement speech, he told a story about a frozen morning in Belgium when a farm kid taught him that regulations were guidelines, not gospel, and that sometimes the best solution was the one nobody had thought of yet. Lieutenant Colonel Harold Benson went on to command an armored regiment in Korea, where cold weather operations were even more challenging than Europe. He made sure every mechanic in his unit knew about thermal circulation systems and encouraged them to innovate when standard procedures failed. I learned in Belgium, he'd say, that the guy with the wrench often knows more than the guy with the manual. Private Eugene Vasquez, who'd helped run copper tubing between frozen tanks while artillery fell around them, became a high school physics teacher in San Antonio. He used Eriksson's field repair as a teaching example for decades. This, he'd tell his students while sketching the improvised heat exchange system on the blackboard, is applied thermodynamics under pressure. No lab, no computer models, no safety margins, just a clear understanding of how heat moves and the guts to try something that shouldn't work. The thermal circulation technique itself had a surprisingly long afterlife. During the Korean War, variations of Eriksson's system were used to maintain vehicle operations in the brutal winter of 1950-51. When temperatures dropped to -30 degrees Fahrenheit and American forces were fighting in conditions that made the Belgian Ardennes look tropical. Army technical manuals by then included official procedures for field expedient cold weather starting assistance, complete with diagrams that would have been immediately recognizable to anyone who'd seen Eriksson's original setup. Even in the 1960s and 70s, as the Army transitioned to diesel engines and more sophisticated cold weather equipment, the underlying principle remained: when you can't warm the environment, warm the equipment directly, using the simplest and fastest method available. There's a broader legacy that's harder to quantify. Eriksson's improvised repair became a teaching case in military logistics courses and engineering schools, not for the specific technical solution, but for what it represented about adaptability, resourcefulness, and the gap between theoretical knowledge and practical problem solving. The story spread beyond military circles. In 1983, a Harvard Business School case study titled Innovation Under Pressure, Decision-Making in Extreme Environments used Eriksson's 30-minute repair as an example of effective crisis response. In 2001, a NASA engineer writing about Mars rover contingency planning referenced the Eriksson principle, the idea that complex technical problems could often be solved with simpler approaches if you understood the underlying physics well enough. The men whose lives depended on those frozen tanks starting, though they never needed academic analysis to understand what had happened. For the paratroopers of the 101st Airborne surrounded at Bas, the arrival of Combat Command B on December 26 meant survival. They didn't know about engine problems or improvised repairs. They just knew that when the situation seemed hopeless, American tanks had punched through German lines to reach them. For the tank crews who climbed into those Shermans on that frozen morning, not knowing if their machines would start, Eriksson's repair meant they could complete their mission instead of abandoning their vehicles and retreating on foot. And for the thousands of soldiers who used thermal circulation systems over the next 4 months of combat operations, Eriksson's ingenuity meant the difference between functional equipment and useless metal boxes. Staff Sergeant Hartley probably put it best in a letter to Eriksson, written in 1946, after both men had returned home. "Karl, I've been thinking about that morning in Belgium. Not the cold, or the artillery, or the fear, but the moment when you asked for a blowtorch and copper tubing and I had to decide whether to trust you. I've decided that what happened that day wasn't really about your mechanical skills, though those were considerable. It was about your refusal to accept the situation as hopeless just because the standard solutions had failed. You looked at the problem fresh, without preconceptions, and you trusted your understanding of basic principles over what the manuals said. That kind of thinking, that's what won the war. Not just superior numbers or industrial production, but the fact that we had guys who knew how to adapt, improvise, and solve problems that shouldn't have been solved. I'm proud I had the sense to let you try. Carl Erickson died in 2003, at age 82, surrounded by grandchildren in the same Iowa town where he'd grown up. His obituary mentioned his military service in a single sentence. It focused instead on his engineering career, his 47 patents for agricultural equipment, and his reputation as someone who could fix anything. The Iowa Gold Star Military Museum has a small exhibit about him now, a few photographs. His uniform, a length of copper tubing, labeled similar to material used in improvised field repairs. Belgium, 1944. Most visitors walk past it without stopping, but if you look closely at the photograph of Erickson in his mechanic's coveralls, you can see something in his expression. Not pride, exactly, but quiet satisfaction. The look of someone who understood how things worked and wasn't afraid to test that understanding when it mattered most. There's a question that haunts military historians. How many crucial moments in war come down to things that never make it into official histories? We study grand strategy and decisive battles. We analyze industrial production and technological superiority. We debate the brilliance of generals and the courage of fighting men. All of that matters. All of that shapes outcomes. But sometimes victory or defeat hinges on whether a 23-year-old farm kid can figure out how to start frozen tanks using salvaged parts and basic physics. The Battle of the Bulge was Hitler's last desperate, gambler massive offensive designed to split Allied forces, recapture the Belgian port of Antwerp, and force a negotiated peace. It failed for many reasons: Allied air superiority, German fuel shortages, the tenacious defense at best, Patton's rapid counterattack. But it also failed because at a critical moment, when a relief column sat paralyzed by mechanical problems, someone refused to accept that those problems were unsolvable. Erickson's story isn't unique. World War II is full of moments where individuals made crucial differences through ingenuity and improvisation. There's the radar technician who figured out how to track German V-2 rockets, the quartermaster who solved the fuel shortage before DAI by repurposing shipping containers, the pilot who discovered how to defeat the German jet fighter by analyzing its turn radius. What these stories share is a common thread: people who understood systems deeply enough to see solutions that others missed, and who had the confidence to act on that understanding even when it contradicted official procedure. Carl Erickson could have followed protocol. He could have waited for the engineers to arrive with their carefully designed preheating equipment. He could have done what the manual said, even though the manual didn't have an answer for his specific problem. Instead, he looked at what he had salvaged: engine blocks, copper tubing, basic thermodynamic principles, and he built something new. In 30 minutes, under fire, in the dark. That's the real lesson of this story. Not that improvisation is always better than planning, or that you should ignore technical expertise. The lesson is simpler and more profound. When you truly understand how something works, you can adapt it to circumstances that nobody anticipated. When you trust fundamental principles over prescribed procedures, you can solve problems that shouldn't be solvable. The Army recognized this. Eventually, the field modification noticed that formalized Erickson's technique was more than just an acknowledgement of a clever solution. It was an institutional admission that frontline experience sometimes produces insights that laboratory testing cannot. For a military organization that valued standardization and procedure, and rightly so, given the complexity of coordinating millions of people and thousands of systems, that admission mattered. It validated the judgment of the mechanics and technicians who actually kept the machinery of war running, often in ways that would have horrified the engineers who designed it. In the decades since, we've gotten better at capturing and systematizing this kind of field innovation. Lessons learned databases, rapid prototyping, agile development, these are all attempts to institutionalize the kind of adaptive problem-solving that Erickson embodied. But there's something irreducible about what happened that frozen morning in Belgium. Something that can't be fully captured in technical manuals or case studies. It's the moment when someone looks at an impossible problem, refuses to believe it's impossible, and starts figuring out what tools they have available. It's the decision to try something unorthodox because the orthodox approach has failed. It's the confidence that comes from truly understanding your craft deep in your bones, so that when the unexpected happens, you don't panic, you adapt. 12 frozen tanks. 30 minutes. One farm kid who understood heat transfer and refused to give up. That's how an entire armored column got moving again. That's how a relief force reached surrounded paratroopers in time. And that's how a small piece of improvised engineering helped shape one of the most consequential battles of World War II. When historians write about the Battle of the Bulge, they focus on the big picture, divisions and armies, strategic decisions, turning points, as they should. But somewhere in the footnotes, if it's mentioned at all, there's a line about mechanical difficulties, resolved through field expedient repairs. 12 words, 30 minutes. One young man who knew how to make things work. Sometimes that's all it takes to change history.